Good evening, all. Welcome to live session number 11 of Computational Fluid Dynamics for Incompressible Flows. Myself, Durga Prasad. So, in this particular course, we have talked about governing equations for computational fluid dynamics, and then we classified these PDEs into different classes depending on how the information propagates as elliptic, parabolic, and hyperbolic equations. Subsequently, we discussed finite difference as a technique that can be used to solve this set of PDEs, and also we analyze how to understand the order of accuracy for a given scheme and stability analysis using von Neumann method. Eventually, we were moved on to Navier-Stokes equation, how to implement this, how to implement FTM with to solve the Navier-Stokes equations. In the last week, we discussed on finite volume method and its differences with respect to finite difference, and we solved the diffusion equation using finite volume method. This week, we will be covering convection diffusion equation, and the next week, we'll close the course with the simple algorithm. So this week, we'll be discussing on unsteady convective diffusion equation, which goes as the general transport equation. You have a rho phi term coming in, and then you have an advection term coming in, followed by a diffusion term. And then we also have a source term. This is the general transport equation, scalar transport equation. And what we are doing now this week is we are assuming u is known. So we are not actually solving for velocity field. Velocity field is given to us. So this is essentially a linear equation in phi that we are trying to solve. So this is just a scalar transport equation where all other quantities are known to us, and we are only solving for phi is the only variable solving for. And in order to do this, we have different techniques. So depending on the order of accuracy, we have depending on order of accuracy, and there is one more parameter of interest here, which we will see now as we go. And with something we already discussed when we were discussing hyperbolic equations, is this quantity that the velocity that you are taking, the when we are solving with a given velocity field. So this is kind of not a pure elliptic equation. So if you just have a diffusion term, it is an elliptic equation. So information or a disturbance anywhere in the domain will propagate simultaneously across the domain. But the moment we have an external velocity field, an advection that is happening, so advection will make sure that there is information propagation in certain directions are uh, faster or better than the other direction. So for example, imagine you have, let's say this is some channel or a pipe or something, and then you have there is some, or you can put an even simple other example is, let's say you have, this is a chimney kind of thing, and then there is some source coming out of here, or maybe the previous example we'll see with that. So let's say you have a container, and then you have something at the bottom. So this something is kind of evaporating. So it is a volatile solid or something, so some camphor ball or something. So whatever is coming from here will get diffused throughout. So that is a pure diffusion case, and it will be an elliptic equation. So it will be spread out uniform. Like initially, if you see it as a function of time, it will become a parabolic equation. But then the moment we have an advection, let's say there is an external field. So there is, instead of this is kind of suspended in some way, and then you have some flow happening here. And when that flow happens here, that the way this concentration profile develops is going to be faster and different from the one than before. So the physics is going to be different, and the choice of this scheme should also be consistent with the physics. So that is what we'll be looking up. And depending on the consistency, we have these two different categories, central and upwind differential. And once you kind of do any technique, then we know order of accuracy is something that we discuss in finite difference. So similar things also appear here for a first order, second order, or this is basically a third order scheme. So with this, we'll cover the quick recap of whatever is discussed in this week lecture videos. Subsequently, we will see some of the previous year problems and some coding examples and how to implement all the above techniques into, I'll use Julia for that. Okay, let's get started. For the teaching purpose, I'll just take a 1D equation. So I have an equation of this form, rho phi plus del x rho u phi is del x gamma del phi del x plus some source term. And this source term, I'll write it as SC. For now, let's say I'll write this source can actually be a function of phi, and this function can be anything. So we'll do some kind of a linearization in it. How do you do linearization? We discussed this before also. If you have some function, so linearization is basically you fix a point phi naught. So I'm going to linearize about this particular point, and what that means is you do a Taylor expansion. So S of phi is going to be S of phi naught. Phi naught is a known quantity, so S of phi naught is again a constant plus phi minus phi naught times ds by d phi evaluated at phi equal to phi naught. So this is going to be a linear function in terms of phi. So this I can write it as SC plus some SP times phi. This is a constant term, and this is the term that is kind of varying with respect to phi. So this is the linear term. So this can actually be replaced with SC plus SP times phi. So this will be my governing equation, and unlike a finite difference method and finite volume, you have to do an integration across a control volume. So so the first step would be we have to discretize the domain. So this is a 1D problem. So I have a domain like this from x equals to 0 to say x equals to some L. Now I'll discretize this into some cells, and each cell center will be my corresponding node that I'll be considering. The nodes will align with the cell centers. So if this is my current cell P, then I have a east cell, west cell, and the phase centers I'll use little e and little w. So this is the way we can discretize our domain. Once we discretize the domain, now we have to do a control volume analysis for any given cell. So if I take this particular cell and I do a integration across this, now I have two different variables here. I have x and t. So we can do an integration with respect to x first, and then subsequently we will do the integration with respect to t. So it will be, again here we're assuming something. I'm taking the integral into the del t, so that because this control volume emission nothing changes over there, I have rho phi dx. Now we can do a little thing, another substitution here. So I'll call, you can see I can take this to LHS, and then I can write del x as one common term. So let us define J as rho u phi minus gamma del phi del x. So which means I can replace this quantity with del j del x times dx is integral dx. Now this is similar. We can use the mean value theorem and the gradient approximation that we discussed in the last week. So with the mean value approximation, we get the first one as del t of rho phi evaluated at point P times delta x, plus the derivative of this will be j east minus j west times the corresponding area. So I'll just write it as there will be a volume integral, so there will be some area term coming into picture here. So if you do the integration, so this will be j at the east face minus west face. So I'm assuming that all of these cross sections, that is the control volumes that I've considered here, are of the same cross section area. So there is no area coming to picture. Otherwise, because when we do the volume integral, I will have an area term here. If area is a function of x, then you have to consider the areas also, which I'm kind of removing here for the sake of brevity. And again, here we have this will be SC times delta x. And then just like before for linear function, we can approximate it with respect to the value at the cell center. So this entire term I'll denote with S bar times delta x, where S bar is basically SC plus SP times Vp. So this is basically the value of S evaluated at the cell centroid. So this we have. Now we have to do another integration with respect to time. So for now, let's start with the study part. We'll only solve for the study part. or I'll also take unstudy together. Let's do the integration also, and then we'll finally see what happens, how it reduces in case of study case. So if you do an integral for time t to t plus delta t, we have rho phi p delta x plus integral t to t plus delta t dt je minus, sorry, this is a del t of this thing. If I do a time integration, so this will become rho phi p evaluated at n plus 1 minus rho phi p evaluated at n times delta x plus je minus aw dt between t to t plus delta t, and similarly on our RHS we have t to t plus delta t s bar delta x dt. So this is straightforward. So this term is basically again just like what we were doing in case of spatial domain. So when we have a function that we want to integrate from xw to xc, we just took the value at a given intermediate value of p is a self-centroid. So similarly, we can do the same thing here. So it is from, instead of xw to xc, this is from t to t plus delta t. So this quantity we will have to evaluate at some intermediate time tau between t and t plus delta t. So that will give us, so this will be replaced with je minus jw, which is evaluated at some intermediate time step tau. Similarly, this thing will be replaced with s bar evaluated at some intermediate time step t, where tau is some time step between t to t plus delta t, which we do not know yet. So there are different schemes that will decide how this tau is kind of figured out with. So, but what we can say is, in general, this will be tau is somewhere between t and t plus delta t. So this value is going to be some linear combination of, so I'll replace this with sigma j at n plus 1 step and n step. So similarly, this I can replace with, so what I'm saying is, if so here what we were doing between xc and xw is we are taking at the self-centered value. So this is basically arithmetic average of east and west x points and then calculate the xp and then calculating it. Similarly here what we are doing is we can choose the value of tau in such a way that this f tau will affect that. So you can, if you choose for example f tau equal to 1, then this becomes this entire thing is replaced with the value from the future time step. So this is an implicit, fully implicit method, just like the Euler implicit method. If ft is 0, then we are only considering the previous time step value. So this becomes an explicit one. And if f tau is half, then this is what, like you have half here and half here. So that is the Crank-Nicolson method. So this is how we do the time integration for our convective diffusion equation in an unstudy form. So now let's say that like we discretize the equation. So now we have some terms, but still it is not in the form of ax equal to b, because we usually have to come up with a form ax equal to b so that we can use whatever techniques that we learned before, say like the Gauss-Seidel method or the direct method, TDMA, all these techniques that we learned before are for a system of linear equations. So this is still not in that particular form. So how do we reduce that? So let's take a simple case so that it will be easy for you to understand how this evolves. So let's take a study case. Unstudy is just an extension of that. So for study case, we have something like this ddx. Let's assume rho is 1, u phi, or I can put rho term also here, no problem. Plus some source term. So this is for the study equation. So just like before, if you do the integration, so we will have rho u phi times some area on the east face. So the cell, the domain is same as before. So you have the current cell, east, west. These are my phase centers. So this is my control volume. So rho u phi evaluated at east face minus rho u phi a evaluated at west face should be equal to gamma d phi dx evaluated at east face, gamma d phi dx evaluated at west face, plus S evaluated at point P times the volume, whatever is the area times delta. So I'll just write it as delta V. So this will be equation from where we started out with. So now let us introduce some nomenclature. So this rho UA is basically something like a mass flux term, which I'll denote it as F. So I'll write F as rho UA, or so that will simplify this a little. So I can write this as Fe times Pe, Fw times Vw is gamma del phi del x. So this we can again write it as gamma E. Again, I'll also have an area term here, which I should have written before. Gamma east, A east times del phi del x, we can use a central difference. So this del phi del x should be evaluated at the east face. So if you are using a central difference which is second order accurate, that will have east and P, because del phi del x is along the x direction. So you have phi east minus phi P by delta x. So similarly on the west face, if you are doing, so it is between P and W. So you have gamma west, A west by delta x times phi P minus phi W, and we have SP times delta V. As evaluated, I'll just write it as S bar, so I'll remove this one so it will be easy for you to understand later. This is just S bar, the mean value of S evaluated at point P. So all we have now is, now let us, whatever we did for the static diffusion, we will use the same notation here. So gamma E AE by delta x, we can call that as the east. See, I'm using little here because all these values are evaluated on the phase centers, times P east minus Vp minus dW Vp minus Vw plus S bar delta V. Now the only problem here is the phi, we are solving for phi values at the cell centers, but these terms here require the evaluation of phi E and phi W, which are at the phase centers. So now we need some kind of approximation that relates the phase center values of the variable with the cell center values. Then that is where we have different kinds of methods. So the first one of them, I'll just write this again. So this is our starting equation. Let me rewrite the equation as in a slightly different form, so it will be easy a little later. So all we have, what we are saying now is, we have some, so if we take this cell volume, this equation can be rewritten as whatever is generated within inside should be equal to the net flux that is going outside from either directions. So whatever is generated within inside is S bar delta V should be equal to the fluxes that are going outside. So what is going outside from east plus, so this is the net flux that is leaving from the east face, minus the net flux that is leaving from the west face is going to be Fw times Vw plus Vp minus Vw. So this is the flux leaving from E phase. This is the flux. So the net flux that is leaving here and net flux that is leaving here, because this has a negative sign, I kept a minus here. Or you can also understand it in a different way. Whatever is the flux that is coming from west to from W to P should be equal to whatever is generated and whatever is leaving out, whichever way you want to understand, but this will be the general equation. So we will take from here and see how to kind of get these values of phi little e and phi little w. So that the first scheme in that is central differencing. So we'll start from this equation and we have our domain. So this is my current cell. These are my east and west phase centers. So the first approximation is a central difference. So what we do here is we will assume that the phase center values are equal to the arithmetic average of the cell center value. So what we are doing is we are assuming that phi east is basically, if you are doing a Taylor series expansion, phi little e can be written as phi p. So we are writing this as, write it in a slide so it will be easy for you. So phi of x east can be written as phi of xp plus delta x by 2, right? Xp is the value for this is xp, so this will be x east. So I can write as phi of xc as basically phi of xp plus delta x by 2. So that will be phi p plus delta x by 2 times del phi by del x evaluated at point P, which is a second order accurate scheme. So now I need an approximation for del phi del x evaluated at point P. Or I can also put a slightly different form. I can just simply explain it in a different way. So you can see this. Oh, sorry. Yeah. So what we are trying to do is phi east. It's again a Taylor series expansion. So I'll write so this is O of delta x square. Now similarly, I can also write phi of xe as phi of this point. I can also write it as xe minus delta x by 2. So can write this as phi east. So if I add these two terms, so this will be 2 times phi east is pp plus phi e plus whatever the residual terms are over here. And from this I can write phi east is basically the arithmetic average of so you can write del phi del x at p minus del phi del x at e. So this is what we are neglecting here. We're assuming that del phi del x is same everywhere. But even otherwise, the point that we are trying to make here is we will approximate the value at the phase center to be equal to the arithmetic average of the values at the other 2 points. So let me write it in slightly different form. I can write phi p. This will be a better way. Phi p is basically phi of xp, which is phi of, I can write xp as xe minus delta x by 2. If I write it in this particular form, so I'll have phi of xc, which is phi minus delta x by 2 del phi del x calculated at east phase, which is second order accurate. Similarly, I can write phi capital E as phi of x capital E, which is xe plus delta x by 2. So that will become phi east plus delta x by 2 del phi del x at the east phase, and which is again a second order accurate scheme. So if I add 1 and 2, the first and the second one, phi p plus phi e is going to be 2 phi e. This term will get cancelled off, and then I'll have a second order accurate scheme. So from this, we are doing is phi east we are approximating as phi p plus phi e by 2, and it is a second order accurate scheme. So this is what we do in a central differencing scheme, so which is a second order accurate scheme. So similarly, phi west can be written as the arithmetic average of the neighboring cells, which is pw plus phi p by 2. Now if we substitute that into our original equation, so we have phi east times phi w, sorry, phi p plus phi e by 2 minus fw phi p plus phi w by 2 is d fp minus fp minus dw fp minus fw plus s bar delta v. Now you can see if I group the terms together to get an equation of the form ap phi p is ae phi e plus aw phi w plus p. So this is the form of equation that we solved when we were discussing Gauss-Seidel method. So I want to convert this into this particular form. So then we will be having a east is the coefficient of east. So I'll take all the terms corresponding with phi p to LHS and everything else on the RHS. So phi east, A east will have a DE term coming from here, and then there is an FE by 2 here that will go on the RHS, so it will have minus FE by 2. Similarly, A west is going to have DW plus FW by 2. The source term will get added to the B term, and then we have an AP, which is the coefficients, all these coefficients taken together. So DE plus DW plus FE by 2 minus FW by 2. So this I can kind of rearrange a little. So I'll write it as DE minus FE by 2 plus, so I have subtracted FE by 2, so an FE by 2 gets added to this, so this becomes FE plus DW plus I'm adding an extra FW by 2 and subtracting the same, so it will become minus FW. So this can be written as A east plus A west plus F east minus FW. So this is basically the net mass flux that is leaving from the cell P, and A east and A west or whatever we have before. So AP can be written as sigma A of the coefficient of all the neighboring points, plus we also have a sigma F, where sigma F is the net flux that is leaving from the particular cell. So this is for the central differential scheme. So now let us see what are the problems with this particular approach. So when we are trying to solve this thing, what we are assuming is just like what we did in the Gauss-Seidel method, that any information from the neighboring cells or disturbances from the neighboring cells is getting propagated into this, and that is how phi p is getting updated. You start with certain values of phi phi west and then update phi p, and then you keep doing that for all the cells. So eventually, after one iteration, information will completely spread across all the cells, and you keep doing it, you eventually reach a solution. So now what happens is, let's take a case where I'll just write the coefficients. Yeah, these are the coefficients we have. So what we are trying to now understand is, let's say you have a cell. This is a cell dimension, and then you have a certain velocity. U is a velocity with which that particular direction is happening. So let's say if there is a disturbance here, some disturbance here, that will eventually travel across the cell, or any other disturbance at the other boundary should come this way, or whichever way it is. There are two mechanisms that are happening here to transport information across the cell. One is the diffusion, two is the advection. Because of diffusion, it will be uniform across the cell, and then because of advection, it will be only in the one direction. So the relative of this, which one should be higher? So we have two things. So I'll say one as the strength for advection, and then I have a strength of diffusion. So because of advection, the flux is going to be rho u area, whatever is the cross section area. So this is the mass flux because of advection. So similarly, the flux because of diffusion is going to be gamma times area by delta x, right? Yeah, of course, you have a phi here coming on the numerator and denominator that I have subtracted out. So the ratio of advection strength to the diffusion strength is something like this. So this we can write it as rho u delta x by gamma. This is what we are calling Peclet number. So what this means is if Peclet number is very high or very low, depending on how you treat it. So if Peclet number is very high, what happens? What do you think will happen? Because we are using Gauss-Seidel method, which is a method that is devised specifically for elliptic equations. So I want this method, this method is particularly suitable for elliptic equations. So this will be applicable as long as we have that elliptic approximation valid, which means the strength of diffusion should be sufficiently higher than the strength of advection. As long as the condition is satisfied, then we are okay with it, right? So which means this Peclet number has to be a certain, like less than certain critical value for this method to work. If it is not, then the solution, like you might get a solution, but that will become unphysical. Or in other words, what we can do is we have to ensure that you have cell small enough so that the effect of diffusion is strong within that small region. So for example, you can think of this as, so if some disturbance is here and this is the because of that the diffusion can spread within inside with a certain thing. So if the diffusion region if the diffusion is kind of expected to be in this entire region, then the cell size should be smaller than this region. So this number will give you an idea of how big the region the diffusion is going to be compared to the advection. So the effect of diffusion, if pure diffusion is very close to this point, source will be very higher. As you move away and away from it, the strength of advection will actually come and dominate that part. So we need to make sure that the cell size is sufficiently small so that the diffusion effects are stronger enough so that our method will be applicable. And one way to do that is this will essentially happen when you have these coefficients as negative. If the coefficients become negative, then then it becomes non-physical in the sense. So the way to get the criteria is, let's say you take the value of AE and you say that AE has to be positive, and this gives you that FE by DE should be less than 2, and this FE by DE is basically my, which is my Peclet number. So this is the criteria that we have. So this critical Peclet number for central difference scheme is 2. So if you are using a central difference scheme, you have to make sure that your grid size, or if I write it in a slightly little different way, I can write it as delta x less than 2 gamma by rho u. So what this means is you have to choose a grid that is, so this I can write as delta x critical. So there is a critical delta x, and only if you take your grid sufficiently smaller than that critical delta x, you can come up with a physical solution. If you take a bigger grid, then you might not get a physical solution. So this we will see little later also again. So this is one aspect of this, and then there is another aspect also that, so we are basically trying to make a form like this, like even use Gauss Seidel or anything. All we are doing is some trick to solve this Ax equal to b system of equations. So when we have a matrix of this particular kind, we need something called a diagonal dominance. You can understand it from when you are solving linear system of equations. We need the rank of the matrix A should be equal to the dimension of the matrix A. If not, then we do not have a unique solution. So the same thing, when we were to write this in this particular form, it will translate to saying that the sum of all the non-diagonal elements to the ratio to the diagonal element. So this should be less than or equal to 1. Of course, if it is equal to 1 for all the cells, this will ensure there is a diagonal dominance, and I also need to make sure that the sum value should be strictly less than 1 for at least one cell, and this will ensure we have a unique solution. Now often there will be some problems which we will see next week when we are solving simple. So there will be some problems where your boundary conditions are such that this particular criteria is not satisfied. So that happens especially when you have normal boundary conditions everywhere. When you have only normal conditions everywhere without any Dirichlet condition, then this criteria is difficult to solve. Only the first one will get solved. So then what we have, then we will have a system of equations for which rank is basically less than the dimension of the matrix A. So which so rank will be less than dimension. Then we need one more additional equation to solve that thing. So which means we need more equations. And we will see that we usually use a trick where we kind of fix some differential and something and fix the value over there, or some sort of trick. So some way to add an additional equation. So the bottom line is if you happen to have a system of equations for your particular case with your particular boundary conditions where this condition is satisfied, but the second one is not satisfied, then you will end up with a scenario where your rank is less than the dimension, so you will not have a unique solution. So to enforce a unique solution, you need to add one more additional equation to the particular problem. And what could be that depends on the physics of the problem. And this criteria is called Scarborough criteria. Yeah, both combined together. Okay, now as I see, like these are the problems with the central defense scheme because it becomes non-physical if you have chosen it sufficiently large grid. So then how do we make it physical? As you see, the reason it is becoming non-physical is because we are kind of having two things that are playing with each other, advection and diffusion term, and we do not know which is stronger in which part of the field. Okay, in this problem, we always know the velocity u beforehand itself. So since we already know the velocity field and we are only solving for a linear equation in phi, we can always calculate beforehand and say that this is the delta x that I need. But usually when we solve the Navier-Stokes equation, u is something that we do not know beforehand. So as u keeps changing, you might either have to use a very fine mesh or you end up having some other errors. So another way to go about this is use an upwind scheme, which is physically a consistent scheme. So what we do here is let's understand what the problem was in the previous case first, and that will kind of directly give reason as to how, sorry, this is west and this is east. And that will kind of give us a way to understand this much better. So as you can see, the problem previously was, so let's say the flow is happening, let's say we figure out the value at the east face. So this is what we are trying to figure out. And what we did previously is we approximated this as, this is what we did. And what this means is the value at the east face is affected by the values at the cell centers P and E. This is true because if the value here is affected by both the neighboring cells, which means it is independent of the direction in which the flow is happening. This is true only if we are having an elliptic kind of equation. So which means the diffusion is stronger than advection. Or I'll just write diffusion advection so it will be easy for you when you revise later. So diffusion term is greater than advection term. But let's say if advection term is stronger. So what happens? So if flow is happening in one direction, so if let's say we'll assume if Fe is positive, so flow is happening in this direction on the east face. If Fe is positive, then information from the east face would not affect the value of the phi at the east face because information is propagating in one direction. So this becomes more like a hyperbolic than a parabolic or an elliptic equation. So because it becomes more like a hyperbolic one where information is propagating in one direction, you have to only use the value of phi from the previous cell, not from the east cell. So phi east is going to be affected only by the value of phi from the p cell. So if phi is greater than 0, then the better way would be to write this as use the value of the p cell. And similarly, if Fe is negative, if the flow is happening in the reverse direction, then the value at this phase center is going to be influenced by the value of this cell instead of this cell. So I have to write that as Fe times Phi east. So this combined together, I'll write in a slightly different way where I'll write this Fe east Phi east as Fe plus. If Fe is positive, then use Vp. Otherwise, Fe plus will become 0 plus Fe minus. If Fe is negative, this term will remain. If Fe is positive, this term will go to 0 times Fe. You can also write it in different other ways. So the lecture videos follows a different notation where you define the maximum of 0 comma Fe and negative of Fe and all of that. But for the sake of brevity, I'll stick to this convention. So where Fe plus is sorry Fe plus is going to be Fe if it is positive. So when I say Fe minus, this quantity will be equal to Fe if it is a negative one, and if this Fe becomes positive, this thing will become 0. That is the notation I'll be using. So similarly, I can write the values on west phase. So I'll have Fw plus and I'll have an Fw minus terms. So Fw plus is when the value at the west phase is positive. So if the flow is along this direction, I should be using the previous cell, so which is Vw. And Fw minus is something like this, then I should be using Vp. Yeah, I think there are no further questions here. So now again we will take a full equation and substitute this and see how our terms with respect to AE, the coefficients change in our governing equation. So let me take the governing equation again. So this is our governing equation. If you plug these terms into the equation, so I'll have so this is my equation. So now I have to pull terms together so that I can write this as APVP is A east P east plus A west P west plus B. So my A east, the terms I have to take on RHS, well that will have AD east, and you can see the contribution from east will only come if the flow direction is in the negative one. So I'll have an Fe minus. Similarly for the west phase, I'll have a DW, and contribution from west will come only if FW is positive. So I'll have an FW plus. B will be the source term, and now I have to club the terms for AP. So I have to take this on the RHS. So I have a D east plus Fe plus DW minus FW minus. So again I can add and subtract Fe minus. So DE minus Fe minus plus Fe minus. Can subtract, add and subtract Fw plus. So this is basically A east plus A west, and then I have my flux terms Fe plus, Fe minus, minus FW plus and FW minus. So this is what happens when we have when we use an affine scheme. So you can see that it is kind of very similar to what we have before. There is an A east and A west term. There is no half term that is coming here, and then we can have AP is basically sigma A and B plus summation of the fluxes that we have. I think this is clear. But as you can see, this is only first order accurate, so we need higher order accurate methods. So why am I saying this is first accurate is, let's say we have, this is my grid again, sorry. So this is my domain. So what do we do now is, what we did previously is, so let's just take phi E and see what happens. So phi E, let's solve for one case, assume Fe is positive, so flow is in this direction. So then we have phi E is basically phi of xc. What we have done is we have assumed approximated from xp minus xp plus delta x by 2. So this becomes phi of xp plus delta x by 2 times etc etc. So this is what we did before. We just assumed phi is equal to phi p, so which is a first order accurate method. So the normal one that we defined before is a first order accurate method, but the central difference is a second order accurate one. So what we do now is, okay, we'll also develop a second order accurate method using affine scheme. So how would that look like? So instead of stopping red just here, if you stop here, it becomes a first order accurate. So I'll expand one more term here. So instead of stopping here, we will write this as delta x by 2 times del phi del x at point P. Then it becomes a second order accurate scheme. Now all I have to do is write these terms in terms of the cell centers. So this will be phi p plus delta x by 2. Again, because I need a second order accurate scheme, I need to use this one, which is at least first order accurate. Otherwise, because we have a delta x already here, so the scheme that I have to use here should at least be first order accurate. I'll use a second order accurate scheme itself, so that eventually the overall accuracy of this particular scheme will become second order. So del phi del x evaluated at P, I can write it as using the central difference in between east and west, where it will become phi east minus phi w by 2 delta x, so that it will be still second order accurate. So if I write these terms together, so this will be phi east, sorry, phi p plus phi east by 4 minus phi w by 4. Now similarly, if f is negative, then we can write phi east as phi of, now if f is negative, then I have to expand from the point, this point here, so that will become x east minus delta x by 2. So that will be phi east minus delta x by 2. Del phi del x at the east point. Again, we'll use a central difference in between these 2 points. So that will be phi east east minus phi p by 2 delta x. So that will become a second order accurate scheme itself. So I'll have phi east minus phi east east by 4 plus phi p by 4, which is a second order accurate scheme. So to sum these two things together, what we'll have is f east phi east will be Fe plus phi p plus phi by 4 minus phi w by 4 plus Fe minus phi east plus phi p by 4 minus phi east by 4. This is the equation I'll have for Fe Fe. Similarly, you can also derive for Fw Phi w and then substitute them back into this equation, and then you will get all this AP, A east, etc. All these equations you will get. So I'm not doing that again. So you can go through, you can do it as an exercise. So that you can try as an exercise. Now again, we can also come up with another scheme. So Instead of why do we have to stop here, we can add one more term also to get the third order accurate scheme. So that is this quadratic scheme, which is a third order accurate one. So this quick stands for quadratic affine interpolation for convex to kinematic scheme. So the idea here is the same as before. So if P is positive, so this is my discretized domain. So what we are doing again, just like before, I'll do for only one case, so you can do for other cases yourself as an exercise. So if Fe is positive, so which is in this direction, so what we can write Phi east as Phi of, so I should be using the one previous value. So I'll write it as xp plus delta x by 2. This will become Phi p plus delta x by 2 del phi del x. Instead of stopping here, we'll add one more term. So that it will become a third order accurate scheme. Now we have to use again, just like before, we need to express these derivatives in terms of the cell center values. And we have to use schemes which are at least second order accurate so that the overall accuracy will be third order. So this will become phi p plus delta x by 2. Same like before, del phi del x at point P, I'll use the central difference. Phi east minus phi west by 2 delta x. So this will become delta x square by 4 times 2 is 8. Del square phi del x square at P. We can use again a central difference. So this will become phi east minus 2 phi P plus phi west by delta x square. So the overall accuracy will be third order. So if I take the terms together, so I have a phi p here and then a minus 1 by 4. So 3 by 4 phi p. And for the east, I have a 1 by 4 here and then a 1 by 8 here. So that will be 3 by 8. Then I have a minus 1 by 4 plus 1 by 8. So that will be a minus 1 by 4 phi west plus delta x cube. Now we can use the same derivation for exercise. I leave that as an exercise, so I don't want to go into the derivation of that. So the same method follows. So you get this equation, substitute them into your into this main equation, collect the coefficients, and then you will get your entire expressions. So that is with respect to the quick scheme. So this is a quick summary of whatever is discussed in these lecture videos. So now we'll quickly go through the previous year problems. So the first question here is the further study convective diffusion equation. The discretized form is written as AP phi p is sigma a n b phi n b plus p, where phi p is the value of the variable phi at cell center. Phi and B represents the values of phi at the neighboring cells. AP and A and B are the coefficients of phi at cell center in the neighboring cells, and B is the source term. U and V velocities are both greater than 0. Peclet number is defined as a ratio of mass flow rate to the diffusion coefficient, just like what we defined previously. And what should be the value of Peclet number for the Scarborough criteria to be satisfied? If this we already discussed, but this to be valid, we need to ensure that the Peclet number has to be less than 2. So we already discussed this, so I'm not going through that again. In a quick scheme, when Fe is negative, the value of VE at the east face is computed using. So for to answer this kind of questions, you can simply draw a grid, and then it becomes easy for you to understand. So this is my P, this is my east, west. It also has a east east in the option, so I'll draw east east. So what it says is F is negative at this east face, so flow is in this direction. So if flow is in this direction, then I have to use the value at capital E. So in quick, what we do is we use the discretization with the neighboring cells around the current point. So first is the general idea is you have to use an upwind thing. So because it is an upwind, it has to derive everything centered around the point E. So quick is a quadratic interpolation, so you need at least the second order derivative will require at least the neighboring point. So I will be using P, E, and east east. So it's all about first you draw the grid, then identify the direction in which the flow is given. From that, decide the cell around which you are doing your expansion. If this is a cell, then take the two neighboring points along with that particular cell. That is what we'll be using for quick scheme. For a known velocity, the 2D steady convective diffusion equation is linear, quadratic, cubic, none of the above. So we have a PDE, but because velocity is already known, so the equation is steady convective diffusion, so which will be 2D. Okay, I'll write in the 2D form. So we have del x, rho uc, del y. So this is the equation that we have that we are solving for. So there is only one variable phi that we are trying to solve for. And sorry. So this is the 2D steady convective diffusion equation. So the variable that we are solving for is phi, and every other variable, every other value here variable is already known to us. So this equation is essentially linear. So if I were to replace phi with say phi star plus some phi naught, like if phi star is a solution to this differential equation, phi naught is also a solution to this differential equation, then any linear combination of this will also be a solution to this differential equation. So of course the boundary conditions have to be accordingly modified, but the thing that we are trying to prove here is this particular equation is linear in nature. Which of the following schemes is less expensive to solve from computational point of view? Implicit, explicit, Cranfield Colson. All schemes are equally expensive. So what is the most computational expensive step in each of these schemes is we are trying to solve a system of equations say x equal to b, or you are simply doing it as x equals to some x naught plus delta t times something. So this we use for all explicit forms, and this we use for the implicit schemes. So this involves solving a system of linear equations. This is just some arithmetic addition, like it's just an arithmetic operation. So explicit methods are always computational and less expensive, but the only problem is they are going to need very small values of delta t. Depending on the problem that you have, for any given grid size, the delta t will be kind of dependent on it. So you cannot arbitrarily choose a large value of time step. So even though each step is computationally less expensive, the number of steps that you have to take to reach the solution to whatever time you need will might be higher. So accordingly, usually even like per step, if you are thinking like per one iteration, so or let me say that you want to go from t equals to 0 to t equal to capital T, and so explicit, let's say, will require 100 steps. Implicit will require, you can actually take a bigger time step with implicit method. Let's say use the same order of accuracy, you can actually use a bit higher time step size from a stability point of view. And if your problem is such that even at that higher time step, you're not actually degrading on your accuracy, then with implicit, you can actually reach in 10 steps. Let's say, I'm just saying. But here, first step, computation is lesser because all you're doing is just something like this, where you start with an x plus x naught plus delta t times some gradient term. This is just an arithmetic addition that you have to do, and you can do that in parallel also. There is no simultaneous equation that you have to solve. But if you're doing an implicit, first step will actually increase because here you have a set of linear equations. Again, you have to use Gauss Seidel or something because direct methods also you like not always possible. Let's say if you're using an indirect method like Gauss Seidel or something, you again have to do multiple iterations within inside it to reach your desired level of accuracy. So computation step increases. So if the question were to say, so which one will take much clock time? So for example, the physical time you want to integrate is from 0 to t seconds, and the actual on computer when you try to run the simulation using explicit, it might take 100 steps where each step is actually 1 millisecond something. The physical time that it's actually taking to do this thing is 100 into 1 millisecond, so that will be 100 milliseconds. Implicit on the other hand, each step might take a longer time, let's say 22 or 20 to 30 milliseconds, so that then 10 steps will be like 200 milliseconds. So we cannot in generalize say, but under the we are assuming that both of them per step computation is what we are asking in the question. If we assume like that, then per step explicit schemes are always computationally cheaper compared to the implicit schemes. But if you want to simulate for a longer time, then the explicit schemes will eventually end up having explosion, or basically they will diverge. So what will you error gets accumulated here? So we will use an implicit scheme of higher order or a higher order accuracy scheme so that you can your stability is not compromised and you reach convergence faster, even though it is computation expensive per step. The idea is this this product is something that matters and which we cannot say, that kind of depends on the problem that you are solving. So here we are assuming that this question is asking per step computation. So as long as it is per step computation, explicit schemes are cheaper from computation point of view. Okay, again we are discussing about quick scheme here. So if f is positive, just like I said previously we did for a negative case, so if is positive, I should be doing my thing around this particular cell. So the neighboring cells will be the ones that will be included. So that will be phi west, Vp, and phi east. The flux vector in the convective diffusion equation for a general variable phi is given by rho u bar phi minus gamma del phi. So this we have already seen. So the convective diffusion equation will have something like this if the source and unsteady terms are neglected. So we can club the terms together and write this as something like this. And this will be my flux term J bar. So where J bar is this term. Which of the following statement describes the Scarborough criteria? Again, this also we already discussed. We need diagonal dominance. So it should be less than or equal to 1 for all the grid points. And for at least one grid point, it has to be less than 1. Otherwise, the rank will become less than dimension and then it will have multiple solutions. So then we have to add one more equation to that system somehow. And that additional equation will come from the physics of the problem, which we will see next week. One trick to do that for certain class of fluid problems. What is the net mass outflow from the three-dimensional cell P where I should have given the diagram also. Okay, sorry, it's my mistake. So let's say we have a cell like this. So let's say this is my 3D cell. That is the back face, front face. So let's keep some axis. Let's say this is my x-axis, this is my y-axis, and this is my z-axis. So accordingly, along y-axis, this distance will be delta y. This distance will be delta x. This will be delta Z, and let's say the cell center is P. Let's call the front face as east, back face as west. So this is the top face, this is the bottom face. So along positive, so this is the north face and this is the south face. So this is how I define the cells nodes here. So then accordingly the net flux will be always along the positive direction it should have a plus, and along the negative direction it should have a minus. So east face is along the positive x, so east is positive, west is negative. Similarly north and south, north is positive, west is negative. Similarly along the top and bottom, top is positive, bottom is negative. In the final discretized equation of 2D convective diffusion equation using first order affine scheme, the coefficient an is, so if you're discretizing around, so north, so let's say this is my grid, so this is my point P, this is my north cell, this will be the phase center N. So how will the discretization look? So if you recall, so how will the contribution for AN will come from the term phi n, right? So contribution from phi n will happen only if advection is happening along the direction which information is carried from the north direction. So which will happen only if the field is like this and the positive direction is along this one. So this is the positive direction. So this will happen only if Fn is negative. Only if Fn is negative this will happen. So the term will have, so it should have Fn with a negative one. And the next question is with respect to plus or minus of Tn. So this flux will always be added in such a way, or will it be subtracted? So that you can understand from here. So what we are doing here is, if you write a diffusion equation for this, so the net flux that is leaving from this will have a positive dn Vp minus Vn, and this will have a negative thing. Write the full equation, then it will be more clear. So the net flux will be F east V east so this will be the total equation. In case of a 2D flow, this will be the flux across flux because of advection, this will be the diffusion fluxes and so on. So now we have to club the terms for phi n together. So if we are taking terms for phi n on to RHS, then we have a dn term here, and then phi n contribution will only come if Fn is negative. So Fn has to be negative, and that thing comes here. So on the RHS it should be minus Fn, and so because it has to be negative, I'm writing this as minus Fn minus. So this is the term that will be going in for the coefficient of An, right? Okay, small correction. All these values are evaluated at phase centers. So this will be little n instead of capital N. Yeah. So because we need Fn to be there only when Fn is negative, it should be this one. Okay, this is the last question. The flux in the west phase center with a central difference scheme for a uniform grid can be written as. So this is again central difference scheme. So you have to use average values of the cells. So this is my current cell. This is my west cell. So this is the west phase. So if you're doing it phi west, so it should have rho u times w west because it is in the negative direction, plus gamma w a w, and we should have an average of Vp and Vw of here, and the derivative here should be gamma times del phi del x at this phase, which will be Vp minus Vw by delta x. So this one. So I think this is a straightforward one. I'm not spending more time on this. Are there any questions in this? Because basically J is rho u phi minus gamma dphi dx. This you have to write at west face times a west will be minus I cap times area. So that will essentially give me minus rho ua on the west face times Pw. I'll write it as Vp plus Vw by 2. Minus minus will become plus gamma A west times Vp minus Vw by delta x. This is the straightforward one, right? Okay, now these are the problems from the previous year questions. Now let us see some coding problems also. So to understand this, like until now we have only discussed how to discretize equation at the interior cells. Now we also have to worry about the boundary cells also. So we'll take a small problem. So 1D problem where you have, let's take a study case first. So you have a problem something like this, u times phi is, let's say gamma to be 1 for simplicity, something like this, plus some source term. Let's keep some source term also. So this is the governing equation that we are trying to solve. So the interior cell discretization is already known to us, so I'm not going into that. Let's only focus on how to do the, and let's keep some boundary conditions also. Let's say phi of x equals to 0 is 1 and d phi dx. Let's take x equal to 1, x equal to 0 to 1 as our domain. So how do these boundary conditions get translated into our set of AE, etc. So the normal equations that we have are, let's use central difference scheme. So we already derived this, that A east is going to be D east minus FE by 2. A west is going to be DW plus FW by 2. B is going to be S bar times delta X. Area we are assuming 1. And AP is going to be A east plus A west plus F east minus F west. This we already know. Now let us see what happens at the boundaries one by one. So let's start from the left boundary. Is a Dirichlet condition. So this is my cell that I'm considering. So this is my current cell center, east. This will be my west face. There won't be any west cell. That is like a ghost point now that we do not know yet. So how do we do the discretization? So we have to do an integration just like before. So the terms will be F east, P east, F west, P west, D east, P east minus P minus D west, P minus PW. This we already know. So all we are doing now is, okay, I'll just write it as delta V. So you can understand that area is 1, then it becomes delta X. So now in this equation, the only things that we do not know now are, for a Dirichlet condition, phi W is phi V and phi W do not exist as such. This is not there. This point itself is not there. So we have to change this term. This term has to be changed. So how do we do this thing is, we have to change this. This equation is derived by assuming that we are doing for an entire cell. So if you recall, how did we get this equation is, we have some term like this, and we did write this as, So this was the term we were having. So we wrote this as gamma A phi p minus phi w by delta x. This is what we did before, but this is not possible now because we have this w point outside the cell. So all we have to do now is we will only consider this half cell and then write the equation for that. So what that does is now this will have phi p minus, instead of taking at the cell center, we will only take the phase center value, which is the boundary value. Because I am taking only half cell, so the distance will be delta x by 2. So this will essentially become 2 times dw phi p minus, instead of west I'll have a boundary value. This will be the only change that will get introduced because of a Dirichlet condition. So the governing equation now becomes phi is Fe phi minus Fw phi b is, this equation remains the same, but now I have an additional dw term coming here, plus the source term remains the same. So if I were to compare the coefficients from this with the other one, so I'll have my east boundary remains unchanged, which is same as before. My west boundary, I'm not solving for any variable on the west boundary, so that should become 0. My source term previously was whatever SB times delta V, but now I have an additional source term that is coming here because of this phi b, which is the Dirichlet condition. There is a flux, there is a constant phi here. So because of that, additional flux comes. And because it's in half cell, there will be a 2 here coming in. So that will be dw plus Fw by 2 times phi b. And what about AP? Whatever AP I have before, this remains the same. Now I have to A east plus A west, where A east, A west, etc. all the values taken from here. Whatever is that, the same remains. But now because we have a half cell, we have an additional contribution here that is coming into picture that we have to take into account. So that additional thing will also get added here, just to take care of the Dirichlet condition. So this is how the boundaries change in case of Dirichlet condition. Only I also have to do what happens for the Neumann condition. So at the right boundary, what happens? This will be very straightforward. At the right boundary, you take the same equation. So we have F east V east, because we are assuming if E is positive. So this will be, okay, let me take new page. So this is the cell that we are considering. So on the west face, on the east face, on the right boundary. So the discretized equation will remain the same, still the same. So you have U phi east minus, we'll write it as F east phi east minus FW phi W is D east times phi east minus phi p minus dw phi p minus pw, and then we have the source term. So this is our governing equation, I mean the start equation that start with. So depending on different schemes, this Fe, Fe, etc. will change. But now the point is, because on the east face we do not have any flux because of Neumann condition, this term will go to 0, because del phi del x has to be 0 on the east face. So this term goes to 0. And what about this Pe? Again, depending on the value of u, this will change. So if u is positive, or I should say if Fe is positive, this equation becomes, or let's say we will use central difference for now. We started out with central difference scheme. So in the central difference scheme, what we can say is, because there is no east cell, so all I can do is I'll just write phi as phi p. So now the equation becomes Fe times phi p minus Fw times Pw minus dw times phi p minus Pw plus S bar times delta V. So if you were to compare the coefficients as before, the coefficient for A east is the one that is going to change, because we are not solving for there is no phi e in the entire equation, so this coefficient should become 0. The coefficient for the west equation remains unchanged. The source term remains unchanged again because there is a zero flux. If there is a constant flux value, then that will accordingly get added into the source term. Now coming to the AP term, whatever we have before remains the same, but because we are now removing the east cell, the corresponding contribution has to be removed from the coefficient. So this is how these conditions will change for the right boundary. So now let's see, this is with respect to the central difference scheme. Now let's say if you are using an upwind scheme, what happens? If for suppose at the boundary FEB is positive, then everything remains the same. So all you have to do is FEFE will become FEFP. So nothing much, but I mean east will not have any variable. But for suppose if FEB is negative, then according to our logic, this should become something like this. But we do not have the value of F east. Because we do not have the value at the boundary, we'll have to be forced to take the value of FP, or we have to use a higher order scheme and then put some ghost cell and do other tricks. So for now, we will take this particular case. This we will leave for now. We are not considering this particular case. We will take a scenario where FEB is positive, such that I can use this condition and then I can use this boundary condition as is. Let's see how to implement this in code. So if you are trying to solve this using your own code, how would that change? And even in the last week, I introduced this thing. We'll do solve this using Julia, which is very similar to what we do. Like the notation is kind of pretty similar to MATLAB, and it will be straightforward with matrices. So here we are introducing the concept of sparse arrays. So the idea here is eventually all the set of equations. So what are sparse arrays? So if you see, we are actually solving a system of equations of the form Ax equal to B. So A will be some matrix, and then there is something we are solving for. So this is usually tridiagonal, pentadiagonal, or there is some kind of structure to this matrix such that most of the values are actually zeros. So if this is of, if you have a 1D problem of dimension n, so this will be a matrix of size n cross n. So that means the cardinality of this particular matrix will be n square times whatever is the size of one element that, like if you're using a 64-bit system, it will be 64 times or whatever, 432 or 464, whatever you are using. Accordingly, this will be the size of that matrix that we need. But most of them are actually zeros that we already know. So why do we have to waste that much storage? So the alternate to this one is a sparse arrays. What we do in a sparse array is we define the array as something like this, where we only store the indices I, j, and v. So I will be a matrix, j will be a matrix, v will be a matrix. So these will be three different arrays. Each array will be of dimension, whatever is the dimension of non-zero elements. So I'll denote that as m. This will also be m, this will also be m. So the total size is 3m, where m is the number of non-zero elements in A. So that will reduce the size of matrix A, and accordingly all our operations can be simplified. But so the only thing is, instead of storing this in the straight simple matrix, we'll be storing the locations within the matrix where the values are non-zero and what is the actual value if it is not equal to 0. These are the three areas that we'll be storing, and accordingly all other manipulations will happen inside. So the problem is same as before. So you have a domain where dx is L by n. Area I'm assuming to be 1. So these are the three arrays I told, I, j, v, that we are storing. Now we have d east, d west as ka by dx, ka by dx, because we are assuming uniform cross section area and then uniform properties. There is no variation. Otherwise, this will be k east, a east by delta xc, k west, a west by delta xw, and so on. F east, fw, again u is constant, a is constant, so this both of them will be equal to each other. Now for the central difference scheme, we have a west as dw plus fw by 2, a east as te minus fe by 2, and ap is a summation of neighbors plus the net flux, and the source term gets added to b term. Now we have to accordingly convert this into our sparse array for different cells. So now let's say for the interior cells, so you have the west cell is basically I minus 1, the coefficient will be minus AW. For the center cell, which is I comma I, it will be AP. For the right cell, which is I comma I plus 1, this will be the east cell, it will be minus A. So now for the west face, which is the Dirichlet condition according to a source term and will be added to AP in this thing. So because we are not solving for anything on the west face, there won't be any addition to AW term. So only AP and AH will be there. Similarly, on the right side, only the west and current cell will be there. There won't be any east cell. So this is how you treat the boundary conditions. And from there, everything else is straightforward. You solve the system of equations and then you make a plot of them. So I've made a comparison with analytical and numerical solution. You can see they're kind of finely accurate enough. So now if you want to change this scheme, so this is same. This is independent of the problem. The only thing that is going to change here is how these values are going to be different if I use a different scheme. So again, you can also try different quantities. So let's say in this particular problem, I have used KS1, AS1, US1, LS1, NS5. So this is the parameters I used. So if I were to calculate Peclet number, which is rho u delta x by gamma, in this case everything is known to us. So u is 1, delta x is 1 by 5 by gamma. This will be 0.2, which is less than 2. So the criteria is already satisfied, so we don't have to worry about it. But let's try one more thing. So we know that Peclet number has to be less than 2. So if we take u value to be say 10, then Peclet number is going to be, or maybe 20. Then Peclet number is going to be 20 times 1 by 5, which is 4, which is greater than 2. So the Scarborough criteria is not satisfied. So let's see what happens if you do that. So if I keep a high value, instead of 10, let's say if I keep 20. Yeah, you can see the solution. You can see the deviation between the solution. So maybe instead of changing this, maybe it's better if you see it from a grid point of view instead of, because analytical solution also changes if I change the grid point. So if u equals to 1, then I need u times delta x to be greater than 2. So delta x should be greater than 2. So I have to use L of at least, say, I'm currently using n equal to 5. So n times delta x should be greater than 5 times 2, so should be greater than 10. So L should be greater than 10. So if my L is greater than 10, then I might have a problem. So let's keep a L value of 20. Instead of increasing U, let's say increase L. Let's see what happens. Okay, it's not readily apparent here. Yeah, but you can try this around. So you can come up with different grid sizes and see how that affects your solution. You can try to vary U, K, all this. I share the core with you. You can try to vary these parameters and see what is effect of Peclet number greater than 2 and so on. Now, as I said, if you want to move to upwind, the only thing that is changing is how these coefficients are calculated. So let's see that also. So in the upwind scheme, we have Fe plus Fe minus Fw plus Fe minus. So just say Fe plus is basically the value of Fe if Fe is positive, otherwise it will become 0. Similarly for all other coefficients. And then we have these things. Everything else remains the same. So the point, and then the solution, if I compare. So this is a solution we got for the same problem using central difference. Now let us see the same for the upwind scheme. You can see that the same grid size I have used, but you can see the error is higher in case of upwind compared to the central difference scheme. You can also, and that is essentially because you are using a first order scheme compared to a second order one. So it requires more number of elements to get the same order of accuracy as the first order one. Like to get the same error, you need more number of elements in case of an upwind scheme. So I leave this as an exercise where this is basically first order one. So instead of this, we also discuss second order, higher order methods. So you can try to implement a second order, third order accurate scheme. Accordingly, these things will change and see what happens. We will discuss that if you have any questions also. But you can try to implement the second order. I'll share this code. You can try to implement second, third order accurate and see how that affects your solution and so on. Let's take it. Now let's move it to the transient case. So all that changes in the transient case is that there are two additional terms that is getting added to AP. One is this so in case of transient problem, we'll have this additional term coming into picture. So because of which we have rho phi n plus 1 n, then we have delta x by delta t. So for the phi p that we are trying to solve, we have this additional delta x by delta t that is coming into our equation, that is coming into the coefficient for p. So that is the additional term that we need to add here, and accordingly there will be this term that is going into the source term. So n, all the values at the previous time step are known to us, so this term will go into the source term and this coefficient will go into the ap term. So those will be the only changes, everything else remains the same. So this is again a fully implicit method. So all we have to do is just like before, we build a sparse system, we solve those sparse equations, but then we have to do this for multiple time steps. Then the solution is something like this. It starts from some domain and it eventually reaches the steady state solution. I think there are no questions in this. Yeah, okay. I have one final question as an exercise for you. Consider this one time. Okay, I'll explain the problem a little. So you have a duct and there is some mass flow through the duct, and at any cross section x, the mass flow is given as mx. Now there is some material inside which has a concentration phi, and then there is phi naught outside. Now these walls are actually not impermeable, but they are porous. Because they are porous, there will be some mass flux into or outside. So accordingly, this mx is not constant. Because these are porous, there will be something going outside or coming inside. So mx is not constant. So mx will change as a function of x, and that is given by the leakage rate. The leakage rate is given by ml. And if the leakage is specified to us, if the leakage is positive, which means it is going outside, then this term phi L will be equal to phi. And if the leakage is inside, that is ml is negative, then you will have phi L equal to phi naught, which is the ambient one. So I'll give some quick hints here as to how to solve this problem. I'll leave this as an exercise to you, but the idea remains the same. So I'll tell the basic idea, and then I'll also share the code with you also. You can try this yourself. So this is the governing equation that we have. So this is the governing equation we have. So first step is you come up with some non-dimensionalization. So this is the domain that we have: x equals to 0, x equals to L, and then we have phi equals to phi 1 here, phi equals to phi 0 that we are trying to solve. So idea is straightforward. So first you kind of non-dimensionalize this problem. You define phi star as phi minus phi naught by phi 1 minus phi 0, or the other way around, whichever is convenient to you. You can write it as phi minus phi1 by phi 0 minus phi1, whichever way. So you non-dimensionalize phi, accordingly you non-dimensionalize other variables also. You will define x star as x by L, and I can also define m star as mx times L square by mx and gamma are of same unit. So this have a here. So mx by gamma, mx L square by gamma a. So these are the non-dimensional variables. Use these non-dimensional variables, substitute in this governing equation and get a non-dimensional equation. I'll leave that as an exercise. That would be the first step. So have already done that. So, and then we also have one more equation, which is dmx by dx is minus ml. Now, as per the question, this once you non-dimensionalize, this will give you m star is 40 into 1 minus x star, sorry. Depending on this condition, x equal to 0, it should be 40, and x equal to L, it should be 0. So because we non-dimensionalize, it will be x star equal to 1, this will be equal to 0. So m star is 40 into 1 minus x. So this means dm star by dx or let's say minus dm star by dx is going to be 40, which is positive. So there is a leakage outside, so I have to take phi L equal to phi, or I'll write this as phi L star is P star. And this will be the governing equation that you are trying to solve for. So if you club the terms together, so it will have something of the sort uh, d dx star of m star phi star, and then you have a source term. Write this as minus gamma a will actually go off once you do the non-dimensionalization. So we'll have d square phi star by dx star square, and then you also have a source term that will be dm star by dx, so that will be something like this. So this will be the governing equation that you will be solving. So it will 5, it will be plus 40, or I think it is actually minus 40. Yeah. So something of this sort will be there that you have to solve for. So I'll show the code for you. You can also go through this again. The only difference from the previous code here is we have x and a accordingly. So u east and u west. So u is not actually constant. So previously till now we have, as I said, we need to know this value. Here the value is known to us, but it is not a constant, but it is a function of x. And that function is what this function is. So u is given as a function that is calculated the east and west accordingly. Because we are storing cell centers, phase center value is obtained by cell center plus dx by 2 or minus dx by 2. And accordingly dE, dW, FW, everything remains the same. All these are same as whatever we have done before. The only thing is when you have a source term, then there will be some changes. Yeah, but otherwise everything else looks the same. So KSP is 0. We just write like this and see what happens. Yeah, these are the different solutions I got, but I'll share this course so you can try the same. The only difference that we have is u comma w are not constant. Instead, they are actually functions of x, and these functions are taken accordingly here. Right? Are there any questions? Yeah, I hope there are no questions. Okay, to summarize, this week we started discussing on convective diffusion equation, where we have an additional u term that is coming here at fraction term, and that value we are assuming that the value of u is known to us, and phi is the only variable that we are solving. So this becomes a linear equation that we are solving. So all we have to do is we have to discretize it on the cell and then get the corresponding equations in the form AP phi p is sigma a n b phi n b plus p. And because we do not know this phi, the values at the phase centers, there are different schemes and how to approximate them, and different schemes have their merits and demerits. The central differencing is where you take the phase value as an average of the neighboring cell centers, and then we discuss an upward scheme where you take the flow also into consideration, and depending on the flow direction, if the flow is along the positive, you take the cell value, you for the phase center you take the cell value in the direction of the flow. So if flow is in this direction, you take this previous cell. If the flow is in the reverse direction, you take the previous cells. Accordingly, whichever is the point that is coming, the information flows from the previous point to the phase. So that previous point is what we will take for an upwind scheme. But because it is the first order, we discussed several higher order schemes also, how to move to second order or third order accurate schemes. I have left some exercises to you, and then we discussed some previous year problems, and we also discussed on how to implement this in code for a 1D case. Expanding it to 2D is also straightforward. Yeah, hope, and that's it. That will be concluding the session. So for next week, we have two things. So one is on 11th April. We are going to have a session from 5 to 7. This is the usual session that we'll have, and we will discuss simple algorithm, which will be very much similar to the MAC we discussed before, that is used to solve Navier-Stokes equations. So this will be the main one. And then we'll also have one more extra session on next Sunday, 5 to 7 p.m. where if possible, if you have any questions, we will discuss those questions. If you do not have any queries, then I would like to actually discuss on unstructured grid or some other problems also, as requested by some of you when we started out this session. So this I'll leave as an extra session that if you're interested, please join the session and we can discuss them as well. Thank you for joining. We'll end the session for today.